Okay, let's go ahead and get started, guys. So we're going to get started while others start to wander in, because the first thing that we're going to do today is our Woo Clap, and today is really a review for your final exam, as well as just taking up some last final exam stuff. Today is really all about what questions do you guys have. So I want you to go back through your notes, spend some time kind of flipping back, and then think, what is the question that you still have? Do you still have questions about something specific to the general linear model, such as something related to linear regression, or related to moderation or mediation, or something related to ANOVA or t-test, or whatever it might be? Do you still have questions from earlier in the semester, maybe something related to reliability or validity, or some of those experimental methods that we've discussed? So take a few minutes, go back to through your notes, and write on the Woo Clap, what question do you still have from this semester that you would like to answer? I may, depending on how many questions there are, I may not get to everything, but I'll try to get through as many as I can within the time that we have. So this is the time for you to start thinking about the questions. Now, this morning, I answered several questions that were put on the discussion forum. So if those were your questions, please go back to the discussion forum, check if you feel like the questions were answered satisfactorily. If not, you can have your chance to follow up now as well. So take a few minutes to go ahead and start writing out what question do you still have that you would like to get answered. Okay, so while people are still filing in and thinking about the questions, I'm going to go ahead and get started answering some of the questions that are coming in now. Okay, so like I said, this is today a review for your final exam. I'm going to go through as many questions as I can that you guys have. Then I'll talk a little bit about what you can expect and what you need to prepare for the final exam. And then we'll do some last minute housekeeping things. Okay? So, first question here. If we do counterbalancing in a repeated measures ANOVA, do we need to present it as a between subjects factor, at least for PL2132? Okay, so counterbalancing is a technique that we do to control for various extraneous factors. Whether you can use counterbalancing in both between and within. So it's counterbalancing is not something that's specific to the design. It is specific to a methodology, or it is a type of methodology that you would employ. So counterbalancing means that you are going to balance out the exposure to something. Okay, there are many things that you can counterbalance. You might counterbalance the order of treatment. So if you have a repeated measures design and you're giving 2 treatments, you might, for half of your participants, do treatment 1 followed by treatment 2. And for the other half of your participants, you'll do treatment 2 followed by treatment 1. This is an example of counterbalancing the order of treatments, but it's in a within subjects design. Maybe you have a between subjects design. You could counterbalance the type of stimuli that you have. Or, quite frankly, you could do a counterbalancing between subjects of order as well. Let's say I have 2 groups, and both groups are being receiving 2 different treatments. For both of my groups, half of my participants get treatment 1, followed by treatment 2. The other half get treatment 2, followed by treatment 1. Now, in general, counterbalancing is something we do within groups. So we want to ensure that the behavior that we see within this group is because of the specific manipulation that we give, and not because of some other extraneous factor like the order of testing. We will counterbalance within groups, but we also need to do this across multiple groups. So each group gets counterbalanced, the order of testing. So counterbalancing isn't really something specific to between or within. It is a method that we do to control for possible extraneous factors. So test order or training order is one thing that we might counterbalance. If I have 2 different stimuli, like I showed you in class, I've got 2 circles, and one circle is always followed by an outcome, and another circle is not followed by the outcome. If my circle is green followed by the outcome, red not followed by the outcome, then I want to counterbalance that. Half of my participants, green is followed by the outcome, red is not followed by the outcome. For the other half of my participants, red is always followed by the outcome, green is never followed by the outcome. So again, the point is that if I see responding that is appropriate to the stimulus where that is always followed by the outcome, I know it's because of the training I gave and not because the circle was green or the circle was red, right? So counterbalancing is just a method that we use to control for extraneous factors that might otherwise explain the results of our experiment. Okay, so next question. In the regression artifact, I can understand why extreme scores move closer to the mean. However, in the case of people with extreme anxiety scores close to the mean, after a while, would it mean that the mean, hang on, let me just read this for a second. Would it be the mean of the people with anxiety or the mean of people without anxiety? Okay, let me see if I can make sense of the question. So regression to the mean is what we could say is a threat to validity. This is another explanation for the results we might get in a design that has two different tests. So we test maybe like a pre-test, we do some kind of intervention, and then we get a post-test. And we see the movement of scores, that in general, one group we see has scores moving maybe upwards or downwards, right? And the question is, are these scores moving because of our intervention or for some other reason? Maybe regression to the mean, where if you test somebody twice, their scores tend to regress to their population mean. Now, if you have a population of people who are highly anxious, their scores are already quite extreme. Okay, you're going to see a regression to that population's mean. And if it is a different population than a healthy control group, then the two populations will have different means. So if I am testing one group here that has extreme anxiety, another group here that has what we say healthy levels of anxiety, lower levels. I test you once at the beginning of the semester, I test you twice at the second semester, or at the end of the semester. And I see that the group that has maybe high anxiety, those scores have gone up. And the group who has the healthy control, those scores haven't really changed perhaps. So I could say there's something to do with what happened during the semester, what they learned, it caused their scores to increase. Or this could be a regression to the mean for this high anxiety group. It's a little bit hard to tell from just this basic design, but that's something to keep in mind. That's another reason or explanation we might have, and another reason we should be a bit cautious about drawing results. So if you have a population where the scores are already extreme, and you see that they become even more extreme, that could be a regression to that population's mean. Maybe they get lower, and again, that could be a regression to that population's mean. If they're two separate populations, you won't necessarily see the high anxiety regressing to the control group population because that's not the same population. We're talking about two different populations, two different means for the populations. So when we talk about regression to the mean, what we're saying is that the scores for that particular population will, on repeated testing, tend to regress to their mean without any intervention. Okay. Each population, though, will have a different mean. So people who come from a population with high scores naturally are going to regress to a higher level. People who come from a population with lower scores are going to regress to a lower score. If that does not sufficiently answer your question, please raise your hand or let me know, and I will try to go back to that. But I think that answered the question. Next question, what does the sum of squares have to do with relating back to the big picture? Okay. So when we talk about sum of squares, this is about general linear model. And the general linear model is, at its core, what is the variance that can be explained by our model relative to the variance we cannot explain? Okay, that's really what it comes down to over and over. That's the F ratio. It's a ratio of how much of the overall variance in the data can we explain based on the means of our groups, or based on the correlation between our predictors and the outcome variable. And then what is the variance we cannot explain because it's due to other stuff that we are not controlling for and not including in our model, right? Individual differences, extraneous variables, just residual noise, whatever it might be. Sum of squares is technically the sum of the squared error. So it's a shorthand for this. So sum of squares is the sum of the difference between if we're talking about the model, the difference between what we predict with the model and what we would predict using the basic model, or what we would say is the overall average of y. of our dependent variable. So the sum of squares, there are two different types of sum of squares, right? We've got a sum of the squared error for the model, sum of the squared error for the residual. So the model sum of squares is the difference between what we predict with our model. So it's the difference between each group mean and the overall grand mean of y, with that difference squared. So it's the error just means difference, right? So it's a difference score. So it's a difference score that's been squared, and we add up all of those different scores for each group, right? So it's a sum of the squared error. So each group, if we've got three groups, we've got three different squared errors, and then we're just going to add those squared errors up to get our sum of the squared error. And this is for the model. For the residual, or the unsystematic variance, we're talking about the sum of the squared error, which is the difference, again, it's just a subtraction, so it's a difference between each observed data point and what we would predict with our model. So we can predict that people in group control might have lower scores compared to people in group 1 had concussion and people in group 4 had concussions in terms of the number of mistakes they make on a math test or something like that. We can't predict why people in the 1 had concussion group still get different scores on math tests. That's the residual error that we can't explain. Now, error is kind of a funny term. Just like significance, error is a misleading term. Error doesn't mean, oops, I made a mistake. Error just means difference, right? So error just means the difference between what we observe and what we predict with our model, which in this case is the group mean. Or if we're talking about linear regression, it's the difference between what we observe and what we predict with our model, which is the correlation, the linear model. That's the sums of squared error for the residual. So sum of the squares is the basis for the general linear model. And then we take those sum of the squared error for the model and for the residual, and we divide it by the degrees of freedom, so that we can get an average amount of error, or a mean of the squared error. So mean squared is just mean or average of the sum of the squared error. And then we just compare the mean squares for the model over the mean squares of the residual. So the sum of the squares is the foundation of your F test. Okay. Next question. Do we need to memorize the degrees of freedom? You need to know. It is helpful to know what the degrees of freedom refers to and how it's calculated, so that when you look at the degrees of freedom, you understand essentially what it's telling you, right? If you see a degrees of freedom for an ANOVA 3 and 128, you understand that the 3 refers to the degrees of freedom for the model, and that's related to the number of groups that you have. The 128 is related to the overall degrees of freedom. So you need to understand conceptually what it is. I'm not asking you guys to memorize formulas. You're not calculating anything by hand. I've made that clear from the very beginning. In fact, don't even bring a calculator. There's no calculation, so don't bring a calculator. So you don't need to calculate things, but you do need to understand, in general, what are the degrees of freedom. The two numbers, what do they refer to? It might be helpful to write down, degrees of freedom for the model is equal to k. Degrees of freedom for residual is equal to n-1 or k-1, because that just might be helpful for you to understand conceptually what degrees of freedom mean. So in that sense, it might be helpful for you to write those things down on your cheat sheet, so that you just have you can remember conceptually what those things mean. Okay, I'll talk about format of the exam later on. In presenting results for ANOVA, it seems like p-value is the most important thing. Yeah, good question. What about things like F ratio, confidence interval, degree? Yeah, good. The F ratio and the confidence intervals, effect size, all of those are important, certainly. When we want to establish whether a model is reliable, then the p-value is the way we generally do it. You can use the confidence intervals. There's no problem with using confidence intervals. In fact, they should be complementary. The confidence intervals gives you a range of values with which you might reasonably expect the F ratio, but the p-value is a quick cutoff point. This is, significant or not significant, reliable, not reliable. They're both good, and in fact, they both are reported. Okay, they should be generally complementary. So it's not like we only look at the p-value. We do look at confidence intervals, and some people prefer to use confidence intervals as opposed to p-values when it comes to determining statistical significance. Nothing wrong with that. I have a tendency just to use the p-value, but I still look at confidence intervals. The F ratio is important, but the actual value is generally not as important as the confidence interval and p-value. Because the F ratio, generally the larger the F ratio is, the more likely it is to be statistically significant, but that doesn't mean that a big F ratio is better and like more important or something than a small F ratio, because it's just a ratio of the variance you can explain and the variance you cannot explain. And if you add more variables and if you add more data, like it just changes the numbers. So you guys have seen when you did multiple linear regression and you did a sequential model, you added one variable at a time, and the F ratio sometimes actually got smaller, but that's okay. It was still statistically significant. So the value of the F ratio doesn't generally matter as much as the p-value and confidence interval. Because sometimes when you add variables, it can make the F ratio smaller, but that doesn't really make the model less. It's not like it makes the model less valid or anything. Effect size is important. We usually only report effect size if we have a significant effect. If you don't have a significant effect, then there's no effect size to speak of. So effect sizes are certainly really important, but don't bother looking at it if the effect is not already statistically significant. Good. So next is, let me see, there's other stuff I missed. T-tests are used to test whether two samples come from the same population. What's the problem with samples coming from the same population, or do we try for samples? Okay. I think I understand what the question is asking. So when we do a t-test, this is testing the null hypothesis that these two groups actually come from the same population, and that our manipulation has no effect. If our manipulation, let's just say I have a group of people who I have given 4 beers to, and a group of people I gave 4 non-alcoholic beers to, and I test your driving skills. If the alcohol has no effect on your driving skills, then my group with 4 beers should come from the same population as the group with technically 0 beers, right? Because the alcohol would have no effect on your driving ability. That's the null hypothesis that the t-test is going to test. The same way that the ANOVA tests whether 3 or more groups come from the same population. Essentially, it's asking, does your manipulation produce a different population of individuals, right? And it's testing the hypothesis that, in fact, all your participants come from the same population, that they all come from the same null hypothesis population. So it is a test of whether they come from different populations. We're always testing whether they are coming from the same population, because if they do, that means our manipulation had no effect. If we see a significant difference, it means that they are very unlikely to come from the same population. And if we've controlled for all of the relevant extraneous variables, the most reasonable explanation is that our manipulation has caused this group of people to be a different population, a population of very poor drivers because of the alcohol I gave them. So it is a test of 2 groups coming from the same population. Generally, we are looking for them to not be from the same population because we are looking for differences between our groups, which would mean that our manipulation has been effective in producing 2 different populations. It is for categorical variables, yes. So we use these to test whether group 1 is different from group 2. Now, if you think about linear regression, we are still going to run a t-test for every one of the predictors to test whether the slope is significantly different from 0. But that is basically looking at whether condition 1 minus condition 2 is different from 0. That is literally what it's doing, right? So the t-test is group 1 minus group 2 over the standard error of that difference. So we are using a t-test to test for differences between groups. T-test is only for 2 groups. If we have 3 or more, that's when we have to start using the ANOVA. But we will follow up the ANOVA with tests that look a lot like a t-test. But these have been adjusted to control for the family-wise error. So t-tests are always one thing versus another thing. It's only for 2 chunks of data. And if they are being conducted as follow-ups, we will correct usually the alpha criterion will be corrected to adjust for those family-wise errors. If I am answering your question and you still have questions, feel free to be like, actually, can I correct, can I clarify something? So feel free to clarify if I didn't understand your question correctly, please. All right, so what is the difference between simple effects, post hoc tests, planned contrast, and pairwise comparisons? Okay, good question. These are all just different ways we can do follow-ups for an ANOVA. You guys know that when we do an ANOVA, it will only tell us that there is likely to be a real difference between at least one group and another group, or at least one condition and another condition. It doesn't tell us which group differs from which group. That's why we do these follow-up tests. Now, we have lots of options for different follow-up tests. If you are, and it really just depends on what your hypothesis is to know which one you should use. I have made a habit of showing you all of the different follow-up tests you can use because I want to show you the different ways and you can do it. But you don't have to do every one of these, right? If I am comparing group control versus both of my experimental groups, then a planned contrast is really useful for that because a planned contrast allows me to chunk 2 groups together to compare against one group. That's when a planned contrast is super useful. If I want to compare group control with group experimental 1 and group control with group experimental 2, I can use a planned contrast and use some kind of like maybe a simple planned contrast. So each group gets compared to my control group. Or I could use a post hoc and only look at those particular post hoc tests. Or a pairwise comparison and only look at those. If I want, so for that sense, you can use any of the above, really. If I want to compare all of my groups to each other, I want to compare group control with group 1, group control with group 2, group 1 with group 2. Then I need to use post hoc tests or just pairwise comparisons because those automatically do all of the different kinds of comparisons while controlling for the family-wise error. So it really depends on what your hypothesis is that you want to test that will determine which of these you should be using. I generally just use pairwise comparisons because normally I'm interested in comparing lots of groups against each other. So that's my usual preference. Or I just use post hocs. I rarely use in my personal research any kind of planned contrast because rarely am I trying to chunk groups together to compare against another group. But it's not, I have occasionally done that. So it really just depends on what you are trying to test, and that would dictate which kind of follow-up you should do. Post hocs and pair comparisons kind of give you the same information. If you get the if you're doing, remember that post hocs are only for between subject variables though. So if you've got a repeated measures design, then you're going to have to use the pairwise comparisons. So post hocs only are available for any kind of between subject variable. That's why oftentimes I just quickly use the pairwise comparisons. They also are, pairwise comparisons are based on those estimated marginal means, which correct for any kind of differences in group size. So they give you slightly more fair comparisons. So that's one of the reasons I also tend to prefer using pairwise comparisons, because they are using those estimated marginal means. But it's not wrong at all to use just simple post hoc comparisons. It's not wrong to use only planned contrasts. It really just depends on what you're trying to test. Okay, let's see here. Next question. So that was, what is sums of squares have to do with, yeah, okay, you answered that one. Okay, so I don't think I answered this fully. So is the sum of squares represent systematic? So I think I did answer it. So the sum of squares has two different versions, right? You've got sum of squares for the residual and sums of squares for the model, and those refer to the unsystematic and the systematic variance. Okay. If our group conducts factorial ANOVA and the interaction effect is not significant, how can we analyze it? If your interaction is not significant, then you would really still be looking at any kind of significant differences within each main effect. So you can still look at for significant differences using those pairwise comparisons within the main effects. I mean, for the purposes of your assignment, you can still be doing this for your interaction as well, just to show that you understand which tests you would be conducting. But usually, if we don't have a significant interaction, we're not going to follow this up with any kind of pairwise comparison. But it also can't hurt to look because the data is there. It takes you all of 2 seconds to scroll down and look at the data. When we talk about dummy coding of categorical variables, could you read so we don't need a dummy code when we're doing ANOVA. ANOVA is for categorical variables. So that is something we don't even need a dummy code. If you're doing, if you're trying to put the categorical variable within a linear model, like when we do linear regression, we have that general linear model. Y is equal to B0 plus B1, X1 plus B2, X2, so on and so on. Then you need to dummy code it. So dummy coding is necessary when you're trying to translate this back into that general linear model format. If you're doing a linear regression with a categorical variable, so maybe you're doing a multiple linear regression, we're trying to predict your final exam score based on the number of hours you study. That's a continuous variable. Fine, no problem with that. Based on, let's say, did you do the reading comprehension worksheets or not? That's a categorical variable. Then we need to dummy code that. We need to dummy code that as a 1 and a 0. Maybe we can have 3 levels. Yes, no, some of them. So we have 2 different dummy codes, right? So no might be the 0, right? Yes would be 1 dummy code, and some would be another dummy code. They always get coded as 1 and 0 when we put this into a general linear model format. So that Y is equal to B0, 1, X1, B1, B2, X2 kind of thing. So when you're doing just a normal ANOVA, you don't need to dummy code it. If you want to translate that ANOVA back into the general linear model, then you need to dummy code your variables. Okay, so for ANOVA, are we required to memorize the steps taken to conduct a one-way ANOVA? You guys will not be doing any SPSS analyses in your exam, but you need to know how to interpret the data. What is the N in degrees of freedom? So when we talk about N, this is the total number of participants. So N here just refers to the total sample size. All right, I'll answer anything related to your assignments, guys, should be put on the discussion forum for the assignments discussion forum. What is the main difference between validity and reliability? Okay, good. So validity is referring to the accuracy of whatever it is you're looking at. Reliability just refers to the consistency. Can we get the same result repeated times? Right. So if we get a result that shows a significant difference between our group who gets alcohol and the group who doesn't get alcohol, if we get a new population, a new group from the same population, will we repeat these results? That in general, our group who got alcohol has poorer driving skills than the group who got non-alcohol. So reliability just refers to the consistency with which we would get a particular result with a new sample from the same population. Now, we can have reliability of many things. So we might have reliability between raters. Are the ratings from each of our judges roughly consistent with each other? That's your inter-rater reliability. And if we get new judges, will they give us, again, a reasonable amount of agreement? If I'm looking at test, retest reliability, are these scores at time 1 roughly the same as the scores at time 2? Okay. So reliability is just about the consistency that you would get something. Now, if something is not valid, it automatically won't be reliable. Because if it's not valid, it means you can't get the same results every time because the thing that you're looking at is not valid anyways. Validity refers to the accuracy or truthfulness of whatever it is you're looking at. If I'm talking about anxiety, I'm looking at construct validity. Is what I'm looking at really anxiety? Or am I looking at maybe depression or just somebody's mood or whatever it might be? Right, so is the construct I'm looking at really accurately reflective of this anxiety that I want to study? If I'm looking at maybe content validity and I've got a questionnaire about anxiety, how well does this questionnaire reflect anxiety? Have I included all of the different aspects or facets of anxiety? Right? How accurate is it? How well have I included all of the different parts of anxiety, and have I included things that are actually not related to anxiety and are not accurate reflections of anxiety? If I'm talking about maybe data analysis validity, how accurate are the results that I have calculated? How accurate do they reflect what's going on in the real world? Have I done the analyses correctly such that when I get a significant difference between my groups, this reflects a real difference in the population? So validity is all about the accuracy or truthfulness of whatever it is that you're looking at, and reliability is about the consistency of getting the same results. What is the main effect of SS mod given all other things remaining the same? Okay. SS mod is, I wouldn't call it the effect of SS mod. SS mod is a reflection of something else. So the sums of the squared error for the model is simply a reflection of the amount of variance in the data that is systematic to our model. So I wouldn't say what is the okay. So the effect of increasing the sum of the squares mod, right? If we increase the amount of variance that is systematic, maybe by reducing unsystematic variance by making sure that our questionnaires are valid, making sure that we have made sure our two groups are very similar. We have I don't know, operation defined our variables, whatever it might be. We have reduced as much as possible the unsystematic variance. We are hopefully going to have a large amount of variance that is systematic to our model. If you think about the F ratio, SS mod translates to the mean squares mod, and mean squares mod is on top, mean squares residual is on bottom. All other things being equal, if you increase the variance that is systematic to your model, you're going to increase the F ratio, which means you're more likely to get a significant outcome. The model is more likely to be significant. All other things remaining equal. Okay. So again, just think about what is the purpose of the F ratio. The F ratio is simply a ratio of variance that is systematic to the model relative to variance that is unsystematic to your model. If you increase variance that is systematic to the model, that's going to increase the F ratio. If you increase variance that is unsystematic to the model, because now you have a whole bunch more extraneous variables that add noise, you're going to decrease the F ratio. So the SS model and SS residual are reflections of the amount of variance in the data that is systematic and unsystematic. And these relate to the mean squares model and the mean squares residual, which are the components of your F ratio. So over and over, I'm saying the same thing. F ratio is simply a ratio of variance explained over variance unexplained. And these can be calculated or reflected as your mean squares model over mean squares residual, which come from the sums of squares model, sums of squares residual. Okay, independence of errors. Yes. Independence of errors is one of those assumptions that we make for pretty much every single analysis, which is that your scores are not related to your scores. Everybody's doing this experiment or doing the questionnaire independent of each other. Because if your scores influence your scores, that produces some kind of dependence, and it biases my results. I am assuming that everybody is doing this experiment by themselves, and they're not like looking at somebody else's paper and copying their answers, basically. Independence of errors is one of the basic assumptions for most analyses. We assume most of the time that people's scores are independent of each other, and that my behavior isn't influencing your behavior, right? Because we're doing this experiment independently. Our behavior is being both influenced by the experimental manipulation, but my behavior isn't directly influencing your behavior. There are a few ways you can check for this. Usually it's just based on how did you conduct your experiment? How did you design your experiment? Did you design your experiment in a way that ensures independence of errors? So if you have everybody doing an experiment, if you put people together in a room and they're able to see and hear each other, yeah, it's quite possible that somebody's behavior might influence somebody else's behavior because you're all in the same room looking at each other, right? So maybe you want to make sure that each person does the experiment by themselves in their own room, right? Or if you have them in the same room, make sure that they're in different, cubicles with dividers. They have their own headphones. So that way, when you do the experiment, your behavior and your laughter about something that happens on the screen is not going to influence your behavior as well, okay? So just the way you design your experiment and the methodology can help can ensure that you have, or at least improve the likelihood that you have independence of errors. Now, you can also test this by looking for all of a sudden I forgot the name of the test. There's a test that gives you, looks for independence of errors, and it gives you, on a 4-point scale, you're looking for the 2, and I just all of a sudden forgot the name. Anybody remember? Durbin-Watson, thank you. Durbin-Watson test. You would get this if you do a linear regression, and you're looking for a score of around 2. That is indicative of independence of errors. But that's just a statistical number. Honestly, the best way of ensuring the independence is through the design. Now, sometimes we know there's going to be dependence. If I am looking at, let's say, the behaviors of people in one family versus people in another family, there's going to be dependence. People in one family are going to be similar, and they're going to have effects on each other relative to people in a different family. So that's a dependence, and so I have to do a different kind of analysis. If you have a setup, a design, in which you expect one group to actually have some kind of relationship with each other, this requires a different type of analysis. We call this a hierarchical or a multi-level model. Way more complex than what we're going to get to in this class. But there are analyses that will accommodate intentional dependence between participants. If I'm comparing people in this class versus people in another class, I expect there to be maybe some degree of dependence because you guys have all been taught by me, versus another class which have a different instructor. And so maybe they'll behave a little bit differently because they all have been taught by a different instructor. So I can model that kind of similarity, but not with the analyses we have been talking about in this class. So independence of errors boils down to each person is doing the experiment or doing the survey on their own. And the behavior is being influenced by my manipulation or by the existing correlation or the existing relationship that exists between whatever predictor and the outcome it is, and not because we're sitting next to each other and your behavior is influencing me. Okay, next up. When can internal validity be applied since this user-determined validity of inferences? Yeah, okay, good. Internal validity at its core is asking about causal relationships. Does variable X cause a change in variable Y? So this is inherent to experimental designs. However, the core idea can still be translated to correlational designs. Is there a real relationship between predictor X and criterion variable Y? So even though we talk about internal validity as about causal relationships, and that is true, technically that is true, you can still apply the same idea to any kind of correlational study. Is the reason we have a relationship between hours studied and grades really because these variables are related to each other, or is there something else that might be influencing this relationship that have produced that correlation? So internal validity is always relevant to any kind of experimental study where you're manipulating a variable and you're looking for causality. Has my manipulation caused a change in behavior? Or is the behavior change due to something else? That's what internal validity is about. But I can still ask the same question about, is variable hours studied really related to grade? Or is there something else that is producing this correlation? So yeah, internal validity can still be applied to a correlational design in this, like in theory. Okay, let's go back up to some of the other questions that have come in. Okay, I'll do a couple more questions and then we will be moving on. Let's see here. What is the main difference between factorial and mixed? Okay, so this is just related to design. Factorial ANOVA is a generic term we use for more than one variable. So a factorial ANOVA, a mixed ANOVA is a factorial ANOVA by definition, because mixed ANOVA means you have at least two variables, one that is between, one that is within. So by definition, it's already a factorial ANOVA. Factorial is simply a word to mean more than one variable, and that distinguishes it from a one-way ANOVA. So if I'm saying I'm doing a factorial ANOVA, I'm telling you I'm doing an ANOVA with two or more variables. Now, I personally like to be more specific. I would say I'm doing a 2 by 3 factorial ANOVA. So I'm telling you, I have two variables. One variable has two levels, and the second variable has three levels. Or I'm doing a 2 by 3 by 3 ANOVA, factorial ANOVA. And I can honestly leave out the word factorial because I'm already telling you, when I'm doing a 2 by 3 by 3 ANOVA, I'm telling you I've got three variables, right? So the word factorial doesn't have to be used for that. It's simply a way to distinguish this from a one-way ANOVA, which has only one variable in it. So if I'm saying I'm doing a one-way repeated measures ANOVA, you know I have only one variable in it. A one-way between subjects ANOVA, one variable. That's all it is. A factorial ANOVA just means more than one variable, more than one predictor variable. So it just means that you have, it could be factorial between, could be factorial within, it could be factorial mixed. That doesn't distinguish it. Okay. How do you analyze confidence intervals along with the p-value? These should be complementary. Okay. Confidence intervals give you a range of values where the real value is likely to fall. That's the easiest way of explaining it. Not 100% correct, but there's a 95% chance that the real value falls within these two, within this range. If the easiest way of saying is if the confidence interval spans 0, so you've got a positive number and a negative number, that by definition would mean that your result is not significant. So the p-value will be greater than 0.05. If the p-value is less than 0.05, then it will not include a 0. Now, the confidence interval gives you more information than just significant or not significant, which is why a lot of people like to use it, because the size of the confidence interval gives you a sense for how much you should trust this result. Confidence intervals that are very narrow gives you a lot more confidence in it. It tells you we're pretty certain that this is the range that it falls within, and it's a pretty narrow range, so we're really certain about this. Confidence intervals that are really big tells you that there's a lot of sampling error and there's a lot of range in which the actual value could fall. So it gives you a sense for how much sampling error there is and how much you should really be trusting this result. If I say that there is between let's say a 90 and 95% chance of rain, you can probably be sure that there's a very high chance of rain, right? If I say there is between a 20 and 90% chance of rain, that gives you a lot less certainty about how much you should trust my prediction of rain. And it's the same idea, okay? So the confidence interval gives you a range of values that helps you determine a bit more the certainty or extent to which you should trust the result. Above and beyond just is it significant, not significant, it gives you that range of here's how much sampling error we have. Okay. But they are complementary in the sense like if it includes a 0, your p-value would be not significant. If it does not include a 0, the p-value would be significant. So use these two as complementary to each other. So the degrees of freedom. Degrees of freedom are calculated for both the model and for the residual. Two different formulas, and it depends on if you're doing between subjects or within subjects. So but basically, the degrees of freedom for the model refers to the number of groups or the number of predictors if you're talking about linear regression. And so the degrees of freedom residual is more about how much error there is. So two different degrees of freedom that you need to calculate, and these will be used to calculate your mean squares because you're going to calculate the sums of squares divided by the degrees of freedom. Why do we do this? Because if I've got 3 groups, the sums of squares is being calculated from only 3 values. It's the difference between the mean of group 1 and the overall average of y. The mean of group 2 and the overall average of y, and the mean of group 3 and the overall average value of y, right? Squared, divided, squared sum multiplied by n. But if I'm looking at the the sums of squares residual, if I've got 130 participants, I have like 130 data points that are being used to calculate my sums of squares residual. So the number of data points that's being used to calculate the sums of squares model is much smaller than the number of data points being used to calculate the sums of squares residual. So, to make it a bit more of a fair comparison, we're going to use the average. We'll divide the sums of squares by the number of degrees of freedom, so that way I'm comparing the average variance explained to the average variance that's unexplained. So the mean square is just taking the average, and that's being calculated using the degrees of freedom. Okay, so I want to get to a few more things here. If I did not get to your question, I apologize. Please do write any remaining questions on the discussion forum. The TAs and I will be answering more questions on the forum. There is a section for week 13 questions. So if your question did not get answered today, please go back there and write your questions now. Okay, so hopefully that was helpful. Now, in terms of your final exam, because there were some questions about this, I don't recall the exact date, but I'm sure you can find it on NUS Mods. You do get to bring one cheat sheet. So the cheat sheet is one page, one side of that page only, and it must be handwritten. Why handwritten? Because the idea of using a cheat sheet is not just that way you have the cheat with you, but also the cheat sheet is intended to help you study. If you write things out, this is going to help you study. By writing things out, you actually encode the information better than just typing, and it's certainly better than just copying somebody else's and pressing print. The cheat sheet is a study technique. Okay, a well-done cheat sheet would mean that you actually don't even need to use it at all on the final exam because you have studied sufficiently by creating your cheat sheet. But it's there as a comfort if you need it. You have it there with you. So that's why it needs to be handwritten, is because I want you guys to think about how will you best put the information from this semester into this one slide of one page in a way that will be efficient for you to find the information, and think about what information is really key for you to know. I don't expect and I don't want you to write everything down, right? You need to go through the semester notes and highlight and pick out what is really fundamental for you to know. How can you best represent this? Instead of maybe just writing out words, can you come up with a diagram or a picture that will illustrate a lot of concepts, so that way instead of having to write down tons of words, you can have one picture that will do it all for you, right? These are ways that you can create a cheat sheet that will be more effective than simply just writing out a bunch of words. I mean, you're welcome to just write out a bunch of words, but the idea of the cheat sheet is to help you study. This is why I insist on it being handwritten. So when you are studying, focus on conceptual knowledge. Again, I'm not asking you guys to calculate anything. Don't even bring a calculator with you. You don't need a calculator. Don't bring a calculator. You need to understand conceptually, what do these things mean? If I talk to you about increasing the unstandardized error, or if I ask you what is the effect of increasing the systematic error, what does this mean? How does this affect the overall result? How does this affect the likelihood of getting a significant result? What does this mean about your the effect of your manipulation? If I ask you about something being, I don't know, not significant, what does this mean about the validity or the reliability? So think about the conceptual understanding. Don't just focus on memorizing formulas. Understanding the formulas is helpful because you need to understand the formula to understand the concept of what that formula means. But I'm not stopping at just, can you regurgitate a formula? That's not what I want you to do. I want to know, do you understand what these formulas are actually trying to do? And when you get a result that is significant or not significant, do you understand what that really means with respect to your original variables of interest? So focus on application of analyses to examples. Again, you're not going to do SPS, like you're not going to go and click through the SPSS menu for the exam. You will see output from SPSS and be asked to interpret what this output means. So make sure you can understand the different tables and what this tells you. You'll be given a prompt and you'll be given an output. So in your own studying, I suggest that you come up with your own examples. You guys have a few different data sets that I've given you as examples. Try to run through and do the outputs on your, or the analysis on your own, and then see if you can interpret what the output means. Okay. Yeah, so focus on more conceptual understanding. Don't just focus on memorizing definitions. Okay. For the final project, I think I've already mentioned, when it comes to doing assumption testing, you just need to write out what assumptions you should test and why. How would you test this? What are you looking for? You don't actually have to do those in SPSS. All right, any remaining questions that you have about the final project can be put onto the assessments discussion forum. The final exam is all multiple response, so it's 35 questions, multiple responses. Each question may or may not have more than one right answer. You guys need to figure out what the right answer or answers are. Okay. Next thing up, I want you guys to, okay, switching gears now. This semester we have been going, talking about statistics and research methods, and one of the things I've been trying to emphasize throughout the semester is that you're not here just to pass the class. You're here to learn something that is going to be vitally important to you. Hopefully you have understood why you're here. Why does the department require that you take this class? Right? It's not just because they want to torture you. It's not just because of some arcane reason. There is a reason why every department, or every psychology department, or in fact, almost every single field has some kind of research methods and statistics class. Because the skills that you learn here are important for continuing in your field, but also beyond just studying and doing research in this field. It's important for how you interpret the events around you in your daily life, in the media, right? It's important for how you are able to think analytically. So one of the final things I want you guys to do is to go on to back to the Woo Club and fill in these answer these questions. So what is something you learned that you in this class that changed how you think about the world? What concept or skills are you proud of understanding that you didn't before? How has learning statistics made you more confident? I used to think statistics was blank. Now I think it's blank. And how has taking this class changed how you see yourself as a learner or thinker? So those are here. Okay. And if you still need the QR code, you can go here. Okay, so what's something you've learned? Yeah. Stats is everywhere. That is true. So hopefully that's something that you guys have picked up, is that it's not just statistics in this class. It's not just statistics in psychology. In fact, we use statistics all the time, whether it is how we think about, what song is going to be on your Spotify playlist, or some kind of governmental regulation. These are all things that are based on statistics. So, yes, can be applied to real life. Controlling for extraneous variables is not so easy. That's correct. Yeah. I think people underestimate the amount of work it takes to create good research. And that's, in fact, why we have a lot of bad research out there. There is a lot of really, really bad research that people put out there, and that is used to justify a lot of arguments. And hopefully what you've learned in this class can help you identify that bad research and be able to say, actually, this isn't a true statement. This isn't correct because the research that it's based upon isn't valid. You didn't control for certain kinds of extraneous variables, so how should we believe you, right? If people are trying to sell you a product, if they're trying to sell you on a position, it's important to think about what is the research that they're using to justify this this argument. Yeah, so other things. Statistics is intertwined. Yeah, and build upon each other. Yes. It's definitely something that builds on itself, right? I think more than many other fields within psychology, statistics really is something that it builds on itself, and it is very much ingrained in all other fields. So if you are studying developmental psychology, you need to think about the research that is being used to form the theories in developmental psychology. And how are those research studies being conducted? How was the data being analyzed? Are they, is the methodology valid? Are the questionnaires that they're using reliable? Statistics is definitely something that is a continual process, and you build on earlier learning. I mentioned earlier multi-level models, and that is simply another type of general linear model that just gets more and more complex. So absolutely it builds on itself. Okay, lots of really good answers, guys. Really good. Yeah, go back and read text, but that's a good thing. So next question, what skills or concepts are you proud of understanding that you didn't before? All right, lots of ANOVAs, good. General linear model, sum of squares, yes, good. So hopefully you guys have understood now the basic concept, at least, of ANOVA, and you can see that it's hopefully not as complicated or as scary as you might have thought. I think a lot of students come into this class thinking that this is going to be like a really scary topic, but in fact, it's the same thing over and over and over again. It's the same idea, unexplained variance, explained variance relative to unexplained variance, wash and repeat, okay? So the ANOVA is really not a complicated topic. It is really the same idea of just we're looking at how much variance is systematic to the model, how much variance is not systematic to the model. Is the amount of variance we have that is systematic a reliable amount given the amount of variance we have that is not systematic? So yeah, things about validity, SPSS, good. So, you may, if you go on to doing research, you may be asked to use SPSS. It is a very commonly used program. Now other softwares are becoming more frequent as well, so it's possible you'll be using R or JASP or something else. But a lot of places do still use SPSS, and even if you don't use SPSS, the skills that you gain from learning how to use it are very translatable or transferable to other statistical software packages. So even if you don't use it, you can still use the same ideas for other packages. Okay. Yeah, good. So ChatGPT, great. Hopefully this gave you a different way of interacting with ChatGPT. That was the whole purpose. It is to teach you about experimental validity. It was also to give you guys another way to interact with ChatGPT that will be facilitating learning instead of just substituting for your learning. So hopefully that was helpful for teaching you another type of study technique. Okay, good. Good. So next question. Whoops. Yeah. How has learning statistics made you more confident and capable person in the world? All right, I see a few funny answers, but good. Yeah, so I'm glad to see that you're not quite as lost in the methods sections. I think, again, when you start to read journal articles, it can be really hard and confusing and tiring. Learning research methods and statistics can make reading the methods and results sections a lot more interpretable, right? And that is really key, because you guys have learned that sometimes people like to stretch their conclusions. So if you just read the introduction and just read the discussion, you might not be aware that the conclusions that they're reaching are not really based in the results that they found. And being able to understand the methods, are these methods valid, gives you a better sense for whether the conclusions that they reached are valid or not valid. So it is really important that you can read the methods and read the results and come up with a conclusion on your own. And then you can judge whether your conclusions about the effectiveness of the manipulation really match with what the authors have said. So, yeah, correlation, not causation, good. Easier to read journal articles, good. Good, yeah, being able to point out statistical fallacies is always a good thing, right? People make arguments on all kinds of terrible logic, so understanding validity is a really helpful for this. Good, so yeah, how to conduct different analyses for different study designs, that's really good. So you guys have learned that different kinds of designs require different kinds of analyses, so that's really good. Yeah, so lots of good answers, some kind of goofy answers, but yeah, good. All right, fill in the blank. I used to think statistics was blank, but now I think it's blank. Okay, I used to think it's hard, difficult, terrible, nightmare, painful. Okay, lots of things that people thought it was. Hopefully not many people think it's even harder, but okay. If you think it's actually harder, this can be a good and bad thing. It is something that requires you to think through it. Statistics is not something that you can just learn overnight and become a master at it. One of the things that you should hopefully have learned is that it does take practice. It does take time. This is not a skill that you learn once, you forget, and you become a master. You need to do constant practice. You need to constantly think about these things if you want to learn it. So yes, it's not hard, but it's something that takes work. And that's something that you should remember. That is just part of doing research methods and statistics, is that it's something that does require work. It requires effort. But that's not a bad thing. Things that are really worth it oftentimes do require work and do require effort. It is logical. Yeah, most of the time. There are lots of times in which we have what we call researcher degrees of freedom. So do I get rid of this participant? Do I not get rid of this participant? Is this an outlier? Is it not an outlier? Sometimes we do have some places in which we have to make a judgment call. but many times there is a logic to it, which is quite nice. Yeah. Takes time to understand, yes. Yeah, all statistics is oftentimes just comes down to general linear models, especially the level that we're talking about. It really comes down to a general linear model. And so it makes it easy because it's the same thing over and over again. Yeah, hopefully more manageable. It does require more than just reading the textbook, but that is super helpful. So hopefully you guys were using the textbook as a resource to help you. Maybe, okay, some people thought it was a bit more painful, but interrelated, yes, good. All right. So some people still think it's a bit hard, but hopefully you found it maybe a little less hard than you originally thought it was going to be, or at least you are able to understand it a bit better then. Okay, last question. How has this class changed how you see yourself as a learner or thinker, even beyond statistics? Okay, yeah, so able to think in a more detailed and logical manner, that's a good thing. One of the skills that taking a course like this gives you is that it helps you to become an analytical thinker. And that's a really important thing, right? It helps you to think about different kinds of arguments or things that people are trying to persuade you of, and to break it down in a more analytical way. One of the previous Stats Matters was asking us to think about how statistics might be related to a future career that you might have, and a lot of people were really surprised about how taking a research methods and statistics course could be applicable to careers that you thought were not at all related to research methods and statistics. Why? Because it turns out pretty much almost every single career still requires you to think analytically, requires you to think logically, and requires you to think about data. And that's what this class is about. So even if you're not going to be doing an ANOVA in your future, having gained the knowledge about ANOVA gives you the skills to think analytically and to think about data in a systematic way. And that will be important no matter what you're doing. So, okay, maybe research is not for you. That's fine. Doesn't have to be for everyone. There's still ways in which you would use these skills beyond research. Because, again, one of the things that hopefully you have learned throughout this class and for the previous Stats Matters activities is that research methods and statistics is relevant even outside of research, right? It's relevant in terms of how you interpret the events around you. So even if you're not going to continue your research, that's quite okay. It's still good that you took this class and gained those skills for how to think about data. Okay, maybe capable of reading 100 pages in a textbook. It's always a good thing to learn. You are capable of doing more than you think you are. Okay. Okay. Fighter, better logic in explaining things. Yes, good, resilient. So, I mean, hopefully this has taught you that you have skills that you didn't think that you had. Yes. You actually are capable of doing statistics. Everybody here is capable of doing statistics. A lot of people come into this class thinking that they are bad at math, that they are going to be bad in this class, but one of the things I want you guys to get out of this is that it's not as hard as you think it is. You are more capable than you think you are. Yes, you're capable of reading a lot of pages in a textbook, right? You are capable of sitting through class and of learning these kinds of topics that might be complex, that might be difficult, but you're capable of doing these things, and you're capable of a lot more than that. Okay. So I think a lot of these they're just kind of silly answers, meow, but okay, so I think that's about it here. Last thing here. Okay, for the last 20 minutes that we have, there are some final housekeeping surveys that you guys need to do. So go on to, I think it's Canvas or something. You would have gotten an email link from NUS to do the course review, so please do that. There's also a quiz on Canvas as a end of semester feedback survey with additional questions that are not on the official NUS, which helps me to make revisions for subsequent semesters. So it's a bit more about your actual experience in the class. So, okay, so for the last 20 minutes, I need everyone to please go onto the NUS page and do the final end of year surveys, please. Okay, when you're finished with the surveys, you can leave. Now, last thing, I did see a number of people who are commenting that statistics is harder than they thought, that they're having trouble, that they're still like struggling. I will remind you guys that I do have office hours. So far, very few people have signed up for them. So if you are struggling, you need to take the first step to come to my office hours. So please sign up. If the office hours I have available on Canvas are not good for your schedule, you're always welcome to email me to schedule a separate appointment. But I want to help you, but I can't help you if you don't take the first step of reaching out to ask for help. So if you're still struggling and really lost, please do sign up for the office hours or email me to schedule a separate appointment. Otherwise, put your questions onto the discussion forum if we did not get to them or if you have additional questions. And yes, your textbook is always a good resource as well to check out. That's it. So please do make sure that you have finished doing the NUS surveys. Please make sure that you have done the end of semester feedback survey as well. That's on Canvas. Okay, guys, good luck on your final exam. Thank you.